Welcome to special series and properties of infinite series. So here are just some sort of series to keep in mind, have around that are convenient. We're going to just give formulas or exact values for what these various series converge to. So first up, we have our geometric series, the sum from n equals 0 to infinity of r to the n. And this is equal to 1 over 1 minus r for absolute value of r less than 1. Again, it diverges for absolute value of r greater than or equal to 1. Next up, we have the sum from n equals 0 to infinity of 1 over n factorial. Turns out that this actually converges to e. Next, we have the sum from n equals 1 to infinity of 1 over n squared. This, in fact, converges to pi squared over 6. Then we have the sum from n equals 1 to infinity of negative 1 raised to the n plus 1, all over n squared. This converges to pi squared over 12. Note the only difference between this and the previous series is that we have added in an alternating sign. Right? That negative 1 to the n plus 1 just makes the terms flip back and forth between positive and negative. Next series we have is the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1. This, in fact, converges to pi over 4. The next series is known as the harmonic series. The sum from n equals 1 to infinity of 1 over n, this actually diverges. This is called our harmonic series. It is a very famous series and comes in handy. However, if we add in a negative 1 to the n plus 1, make those alternating signs, the series does converge, and it in fact converges to natural log of 2. So this is referred to as the alternating harmonic series. We had a math joke at my college in the math majors that if a casino or lottery wanted to pay out a large prize, they should pay out using the harmonic series. So they could start off by paying you $1 the first day, and then a half of $1 the next day, and a quarter of $1, or sorry, a third of $1 the following day, and a quarter of $1 the next day, and go on forever. Technically, if they kept giving you money for infinity days, they would give you an infinite amount of money. However, to the lottery winner, it would not seem like you're getting much money at all. So the harmonic series is a famous one. It does not seem like it should go to infinity, but it in fact does. All right, so now let's move on to some properties. So the scalar multiple rule says that if C is a constant, then the infinite series, the sum going from n equals 1 to infinity of C times a sub n is exactly the same thing as C times the sum from n equals 1 to infinity of a sub n. So if the sum from n equals 1 to infinity of a sub n converges, then so does the sum from n equals 1 to infinity of C times a sub n. And this is the rule for finding it. We also have the sum or difference rule. So essentially, if the sum from n equals 1 to infinity of a sub n and the sum equals n to infinity of b sub n, if both of these converge, then if we take the sum from n equals 1 to infinity of a sub n, either plus or minus b sub n, whichever one you want to take, this is exactly the same thing as taking the sum from n equals 1 to infinity of a sub n, and then adding or subtracting, whichever you were doing, the sum from n equals 1 to infinity of b sub n. So as long as we have convergence, we can split series across sums or across multiplication by a scalar. It's key that we have convergence of the pieces that we're splitting up. So for example, let's find the sum of the following infinite series. So we have an alternating series here. We're taking the sum from n equals 1 to infinity of -1 to the n plus 1 times 2n minus 3 over n squared. So this should be the same thing as the sum from n equals 1 to infinity of -1 to the n plus 1 times 2 over n. And then we have minus -1 to the n plus 1 times 3 over n squared. So notice we have alternating series for both essentially a 1 over n and an alternating series for 1 over n squared. So we have alternating series for both of those. There's our alternating series for over n squared converged and our alternating series for over n converged. So we're going to go ahead and just rewrite this. We will split this and pull out a 2 from the 2 over n. So this becomes 2 times the sum from n equals 1 to infinity of -1 to the n plus 1 over n. Then we have minus 3 times the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared. Again, scrolling back up, the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared was just pi squared over 12. And the sum from n equals 1 to infinity of -1 to the n plus 1 all over n was natural log of 2. So this is simply 2 times the natural log of 2 minus 3 times pi squared over 12, or 2 times the natural log of 2 minus pi squared over 4. So this is how we can go about using those rules and using some of the series that we do know to evaluate what a more complicated series converges to. Obviously, this will not work for all series. These happen to split into a combination of series that we did know. So this was one that we could evaluate using previously known series. All right.